Right, ladies and gentlemen, 4 p.m. Central European Time. Welcome to a new Synera webinar. And today it's about bridging the gap between design and manufacturing. The design of metallic components often faces a critical challenge: the lack of integration between the design phase and manufacturing processes. Designers frequently lack detailed knowledge of specific manufacturing methods, knowledge traditionally acquired only through hands-on experience in production. This gap limits the ability of engineers to achieve the ideal first part is the right part approach and places an unrealistic expectation on them to master the wide range of expertise. In this webinar particularly, hosted by Synera, our partner TECNALIA will delve into how advanced computational methods and holistic design tools can address this challenge. We will introduce eCast, an add-in developed within Synera, which integrates with CAM tools to predict the optimal casting system designed based on various success criteria without having to rely on the expertise of the foundry operators. And as you can see, we have two experts with us today. One being Ignacio, who has completed his doctoral thesis focusing on bio-inspired design and manufacturing methodologies for lightweight, functionally customized and sustainable metallic components. His current work involves the advanced computational design of metallic components for diverse functionalities, including structural performance and thermal management. And last but certainly not least, we have Sebastian in the session as well. Sebastian is Customer Success Manager at Synera and ensures that customers of Synera reach their goals through process automation. He studied mechanical engineering and worked 11 years as development engineering and project leader in innovation and digitalization at EDAC Engineering. At the end of the webinar, we have time for all of your questions, but feel free to ask your questions already during the webinar and put them in the Q&A box or chat inside of Zoom, so we're able to answer them all one by one at the end. And we'll kick it off with a question: how do companies benefit by bridging the gap between design and manufacturing? And with that, I'm going to hand it over to Sebastian.
Yeah, hi everyone. I guess that there are some people I've never heard of about Synera, so maybe first a quick intro about Synera. Synera is a software to automate manual processes in your engineering, and you can use our visual low-code language to visually program your workflow and execute it automatically. You can use your existing tool stacks and connect it to Synera so that you can automate your existing manual tasks by using Synera. And yeah, and this is the way how TECNALIA and all other customers are bridging the gaps between design and manufacturing, but also between CAD and FE simulation or other domains. And this is how we achieve great KPIs and that I want to show you. And yeah, so how do our customers create revenue or create a return on invest by bridging the gap between design and manufacturing? And as explained, so the bridge itself is Synera. So it's a digital bridge between the design processes and the manufacturing. And I checked all our use cases, like over 50 use cases, and what they all have together is how they create revenue for our customers. And we can distinguish between the design process savings, so that automation creates value there, and also automation will create revenue, gain profit in the manufacturing process or directly in the product later on. And one obvious thing is if you automate workflows that you would usually do manually, you'd definitely save workforce. And we figured out that the average saving we can achieve here is 76%. So 76% of the time that you usually spend manually, you can save through automation with Synera, especially by having use cases in the design for manufacturing. And now don't be afraid that you lose your job if you automate, but most of our customers use then the free time to do better stuff, to do more engineering. And Ignacio, I hope you can also tell that you're still working besides you automated a lot of your tasks.
Sure. Hi, everyone, and thank you, Sebastian and Synera, for having me today in the webinar. I think the ROIs that we can achieve with Synera are quite interesting. We actually work a lot by automating our design algorithms, not just for CAD design, but also for FEA analysis or manufacturing simulations. So keep in contact with Synera, which is a very interesting collaboration between TECNALIA and Synera.
Yeah. And one more thing, how you can create profit is by capturing your knowledge. So once you automated a process, you also capture the knowledge. So for example, our customers digitalize the best practices. What do you do if you have, for example, a hotspot? What are the design requirements? What are the draft angles? All those tricks and processes you can also digitalize and capture in an automated process. So if an employee is leaving your company, your knowledge is not leaving as well. And this is also how our customers create value. And one big point in the design process is for our customers the reduced time to quote or the reduced time to start of production, especially if you have to quote in the RFQ phase. I think also you have, for some people it happened that you exceeded deadlines, so you lost the whole opportunity just because you were too slow. And therefore it's crucial to have automation, especially nowadays in the FQ phases, and to fulfill the deadlines and also to speed up the time until the start of the production. And last but not least, on the design phase, reduced quality issues and error costs can add high value if you automated a process. If it's qualified and tested, those processes, you won't have errors that you usually have if you do things manually. So less warranty costs. And one example from our customer, Freud, showed that they increased, for example, the simulation utilization by 50%. So the maturity of the design is increasing, and you're having less errors and error costs later on. And also on the side of the manufacturing and also on the side of the production, you can create a lot of return through automation. For example, what is quite obvious is if you reduce the weight or improve the performance of your part, like the stiffness or the thermal behavior, what you see later from Ignacio. And but one maybe major big thing is saving production costs, the holy grail. Yeah. And one obvious thing is if you reduce weight, you reduce material consumption, and you therefore reduce, for example, the production costs. And you have a big impact by automating, by bridging the gap between design and manufacturing, by reducing the later on production costs. And reduce time to market, very important. So if you use less prototypes because your design is more mature and you enter the market earlier, for example, especially for the OEM, it's important to improve the competitiveness and increasing the market fit. And last but not least, also in the manufacturing process, if your design is more mature, if you don't need more tests and you don't have to change the tooling, you can save a lot of time and cost there through automation. And how this all works, I'm happy to have Ignacio here we will show you some real-world examples how all these possibilities create value through bridging design and manufacturing.
Yeah, thank you, Sebastian. So let's go ahead to see some real examples on how to bridge this gap between design and manufacturing. First, I would like to introduce a bit TECNALIA. TECNALIA, for those who don't know, is the largest center for applied research and technological development in Spain. We collaborate with companies and institutions to improve their competitiveness, and we work in a lot of industrial sectors. But in my case, I work in a group which is called Firmetal, which goes for alloys, components, and metal circularity. Here, we work for metallic components, and we try to address a lot of things in the cycle. Let's say that we are able to design and manufacture special metallic alloys. We are able to do very advanced computational design and manufacturing with advanced manufacturing processes for metallic components. But we also have the part to treat with thermal, mechanical, and thermomechanical treatment technologies to recovery, recycle, and revalorize the critical metals. We also have, we do all this in our pilot plant in Irún, near San Sebastian. So let's go ahead and see which are the modern challenges in engineering, right? So one of the big challenges is that the technological demands show the need for components that are more specialized, lighter, and and to reach the market faster, right? So to meet today's needs, companies must put efforts to specialize more in computational design, but not only, also in advanced manufacturing processes. Another major challenge here in the traditional engineering process is the disconnection or the lack of connection between design, manufacturing, and validation of the metallic components. Right now, these stages are often done separately, which makes the process slow and inefficient. For example, let's imagine an engineer that may design a part based on its experience, right? So he chooses or she chooses a material without fully understanding how manufacturing might change its properties. And then someone else runs the simulations to test the design. Another person creates a prototype, and yet another tests it, right? This back and forth takes a lot of time and involves many people, making the process very complicated. It's clear that a better and more connected approach is needed. So even on top of this, we are seeing that factories are losing experienced workers, and much of the knowledge that used to come from years of experience is disappearing. This makes the process even harder. So the solution that could overcome this problem is a holistic process where the first part is the right part is achieved. This means that having tools that connect design, manufacturing, and testing into one process could resolve this question. But there is an extra complication here. While it might seem that one person could manage everything with right tools, it's not that realistic to expect that this single person to know everything about every stage. So that is why it is so important to use specialized and automated tools. These tools make possible for someone with basic knowledge of each stage to successfully produce a high quality part on the first try. So let's go a bit deeper into the traditional engineering process to see this problem, right? So we see that we have this linear process in which we start designing the component based on experience. We perform this operational analysis. We design the complementary elements for manufacturing the part, and we do a prototype, or we manufacture a prototype, right? But every time we see an error in one of the stages, we have to go back and forth with other people in our company to solve the issues, being a very iterative and inefficient process. So the holistic solution that is proposed by us is to use, for example, the platform IGME by TECNALIA, which helps to predict the material properties based on composition and manufacturing processes, but also to optimize those alloys in terms of composition in order to achieve the best solution possible. If we work together with this platform, with, for example, advanced computational design tools like inspired design, simulation-driven design, topology optimization, generative design, all those methodologies that we know. If we also use the operational analysis, these multiphysics simulations to predict the behavior of the optimized component, and finally, we could use also the design for manufacturing simulation, where we apply the manufacturing restrictions and automate design of the complementary objects needed since the design phase, and also analyzing the behavior of the design in a computer-aided manufacturing simulation tool. We also have the capabilities in TECNALIA to use several advanced manufacturing techniques for manufacturing prototypes. Let's say, for example, additive manufacturing, assisted gravity casting, investment casting, additive manufacturing, other manufacturing processes in our pilot plan. So now I would like to introduce you the use case that we are going to present today. We have seen that the technological demands for the thermal management components in certain industries, such as electric mobility, hydrogen-based developments, and high-performance electronics, which also have a lot of applications in different industries, such as space, automotive, and aeronautics, need a very high tech optimization in order to achieve lightweight and efficient components. These usually come with complex geometries that are hard to manufacture, so we have to develop advanced manufacturing methods and know how to use them. So the use of material property prediction is also very important in terms of the manufacturing process that we're going to use, or we are planning to use for manufacturing our prototype, the composition of this metallic alloy, and the operating temperature of the component itself. Finally, again, we could use the design for manufacturing and simulation of the manufacturing process. Now, let's deep dive in a live demo of inside our IGME by TECNALIA platform, but also in Synera. So here you can see IGME by TECNALIA platform. It's IGME because of integrated computational material engineering, which is a methodology that connects multi-scale simulation tools. Its goal is to establish relationships between the chemical composition, manufacturing process, the materials microstructure, its properties, and its performance. This approach, known as PSPP, for Process Structure Properties Performance, is validated through experiments to ensure the accuracy of the models. IGME by TECNALIA is a platform that integrates advanced models and automates their connection. It is structured into three main modules: the simulation module, the experimental analysis, and the database connection. Following this PSPP approach that you can see in the screen, the platform includes specific models for each stage. For example, for process, we have additive manufacturing simulation tools using FEM, for example, for SLM process. For microstructure, we have also different models such as CalFAT, FEM models, or phase field models. For example, for properties, we have hydrogen diffusion models, CalFAT models, FEM models. And for performance, we have connected IGME by TECNALIA with Synera for having or doing easy structural analysis. So if we want to set up our simulation for our use case, we want to predict material properties based on manufacturing processes and chemical composition. So we will select the CalFAT model in order to achieve this. So if we set up the simulation, here you see in the left-hand side of the screen, you have the setup simulation instructions, and in the left-hand side, in the right-hand side, we have the optimization setup. So if we set up our simulation, we click there, we'll see that we have an open document in which we have the important parameters for the simulation, which are the composition of the aluminum alloy in this case, and the cooling rate dependent on the manufacturing process. So now, if we go and run the simulation, we will see how different data files are created and how these results are shown into different solutions. Now let's go to Synera. Here you can see our workflow for this use case, which is fully developed by TECNALIA. You will see, well, we will start by analyzing the geometry creator. Here we have developed a creator for heatsink geometry. We will explore different cases. First, the bio-inspired design case, which is based on the thermal regulation of elephant's ear vessels, for example, or the tree's roots. But we will see a traditional case in order to compare both, which is based on rectangular shaped fins. We have selected investment casting as the manufacturing method because of the complexity of the designs. So the minimum allowable thickness is set to 1.5 millimeters. We have selected the heatsink side dimensions to be 100 millimeters. We have a radial spacing for the tree structure for the bio-inspired design. And we also have the thickness defined to 2 millimeters. Now we will see the results or the geometrical results of the bio-inspired heatsink, you can see there, but also the traditional heatsink. Now I would like to start by showing the steady state thermal analysis for aluminum alloy for investment casting A357, that we will see the comparison between the traditional result, which is 258.3 Kelvin as minimum temperature, and the bio-inspired design has 257.3 Kelvin temperature. So clearly outperforms bio-inspired design to the other one. Now let's go to the material properties prediction with ICME by TECNALIA. So as we were mentioning, we can predict the properties based on composition, manufacturing processes, and operating temperature. Here we have selected 3 different manufacturing processes: the selective laser melting, gravity sand casting, and investment casting. 3 of them can be selected with the index that you see there from 0 to 2. And as the input for this component, we have also the composition of the aluminum alloy for investment casting, which has to be ordered in that way in order to the workflow understand it accurately. And we also have the operating average temperature. Now, we would like to perform the same steady state thermal analysis for the 3 different manufacturing methods in order to see how the outcome change. We have the inputs of the density, the thermal conductivity, and the specific heat capacity to perform the analysis. You can see there how our, in investment casting, we achieve 249.8 Kelvin as minimum temperature. For gravity sand casting, we achieve 249. And for SLM, additive manufacturing process, we have 250.9. So with this, we can first observe a significant difference in the performance of the generic material properties obtained from a database compared to those predicted in our workflow. And second, we see how there is a variation in the results for each of the manufacturing processes. In this case, the best solution is not investment casting in terms of performance. We have seen that the minimum temperature is for gravity sand casting. But as it is very challenging to manufacture this part in this way, we have selected investment casting. Now, to keep on, we should design the casting system. We need to design the gating system with some geometrical rules based on theoretical parameters. We need to design a ceramic core which will define the negative geometry of the part and the casting part. The cell that is designed usually for investment casting will be designed in Procast. Here you see the whole assembly, the gating system, the casting part and the ceramic core. And now it is very important to mesh our geometry with accurate mesh, but also in a way that Procast is able to understand our different volumes. So now let's go to Procast. Here you can see in different colors how Procast is able to understand our mesh. This is what we were looking. And we have to perform the volume mesh and also to design the cell for investment casting. You can see there the cell. Now, let's see the results. First, you will see the video or the simulation of the temperatures during the filling. You will see how in the tip of the fins of our part, the melt starts to cool, but in the end, the parts seem to fill correctly. You will see also in the next simulation, which will be the solid fraction of the part. You will see how also in the tip of those fins, it will start to solidify before filling completely, but in the end, it seemed to feel completely without problems, as you can see in the gray parts where the solidification is started. So here you have an example on how to use this kind of holistic design. But we also have different examples. For example, we worked a lot with different structural components. In this case, we are presenting here BioFly project, which was made in the OASIS consortium with the partners of the University of the Basque Country, Alfred Wegener Institute, and CEA, where we redesigned and optimized an aeronautic assembly column. Yes, Sebastian, do you have something to add?
Yeah, what would happen with those workflows if I now say like, hey, we have to change the material? How much effort would it for you to find a new design that works?
There should be no problem because, well, right now the workflow is developed for aluminum alloys. So we could change the composition of any aluminum alloy to achieve our desired material property prediction. But we also have different models for example, for steels or more special alloys. So it shouldn't be a very high effort to change the materials.
So no added manual effort, also no really added manual effort than conventionally. Yeah.
Of course, yeah. If we would do this all manually, we would have to do all the stages one by one manually. But in this case, with the automated workflow, we are able to perform it just in seconds.
Nice.
Yeah, so let's go ahead and keep explaining what BioFly was. We are, well, as I was mentioning, we try to redesign and optimize the columns that you can see in the upper left side because of, well, to achieve lighter structures and vibrationally optimized a component. I think it will be easier to see in a video that we prepared. Here you can see how we used also Synera for our design. We used the load lines from topology optimization to apply a dragonfly wing pattern in our lateral blades of our structure. We did a comparison between many different designs, but in this case, this was the best one. Here we can see the validation of all the vibration modes, but it is also very important, as I was saying, the casting design to achieve the best part possible. So here you see how we also perform the simulation of the part, we filled it correctly, and we also, when we saw this simulation, we started with the manufacturing of the part, as you can see in the image. You will see here how we manufactured the mold via binder jetting technology. This is how we assembled the mold. It was quite complex because of the tight tolerances, and we had 24 parts of sand. As you can see, the part has a considerable size. Now you will see how we melted the whole quantity of aluminum, how we poured into the mold in the next video here. And you will see also how it filled perfectly or completely the part. Yeah, there you see. And this is the final result. You will see also the demolding operations that we had to do. You will see here how it was. It was like more like an archaeology operations. All of this was done in the pilot plant of TECNALIA. So as you can see, we have the capabilities to produce very complex parts, not just with casting. So this is the KPIs that we obtained: a 70% weight reduction and improved vibrational behavior of the original structure. We also have other examples, such as this one, that it was a development of or a proof of concept of a gyro-based heat exchanger. We are now working in a more complex one, but this is also a proof that the thermal management components have to be further developed in order to achieve the technological demands. We manufactured this part with binder jetting technology, also in TECNALIA. And finally, I would like to introduce you an add-in that we are right now in development, which is called ECAST, which in essence is or will help in the future, because it's in development, in the future will help engineers to achieve or to have an automated tool to design the casting supplemental elements. This goes in the path with the things that I was saying before about the to achieve or to avoid the problem of the lack of knowledge or the experienced workers in factories, and to give to one person, to one engineer, the capabilities without knowing very much about the process itself, to be able or to be capable to achieve good casting designs. So how does this add-in work right now? We have the flow diagram there. We have a first component or a first node inside Synera, which helps dimensioning the risers theoretically. Then we have a builder, geometry builder, where we build the geometry of the neck and the riser itself. We have a measure to, as in the workflow that I've already shown, to let Procast to understand the geometry that we are exchanging. And we have also a Procast launcher where we are able to perform inside Synera Procast simulations where we have as an output right now the average porosity of the part. Finally, we have an optimizer in which we can select the response that we want to optimize in order to achieve the best dimension possible for these risers. As you can see in the bottom side of the image, these are the parts that we are able to manage right now. But as is in development, we are planning to use more complex parts, but we also are planning to not just stick to the riser dimensioning and positioning, but also we would like to start by helping engineers to design gating and filling systems.
Yeah, thanks, Ignacio. Awesome use cases. I think now for everyone it should be sure how to really create those great KPIs, weight savings, knowledge capturing, and so on and so forth. And yeah, I'm happy that you also will provide those for our use case database that I would like to introduce here. So everyone who's interested in seeing more use cases from Ignacio, from TECNALIA, from all our customers, I highly recommend to visit our website and check out our use case database to find a lot more use cases about bridging the gap between design and manufacturing and all the other gaps that we have in engineering. And yeah, then I encourage everyone to reach out to Ignacio and to me and to identify your saving potentials. And yeah, looking forward to that.
Excellent. Thanks so much, guys. And I think with that, we can move over to the Q&A section of this webinar. I'm just going to stop sharing the slides, turn on the camera, and I'm going to check in the Q&A section if we have some questions coming in. Let me check. Question number 1, why alloy design in combination with process automation matters? So what challenges, some of you already mentioned, Sebastian and Ignacio, what challenges do industries face in aligning material properties with manufacturing and operational needs? Whoever wants to go first.
I can go first.
Okay.
So I think, as I was mentioning before too, I think there is this lack of integration between design and manufacturing stages. Because we have in traditional engineering companies a lot of people involved in this process. So this disconnection makes very hard to understand what is happening in the whole process. So sometimes we have to go back and forth and make this iterative process to achieve the best part. But also, I think in more modern way, as we try to give to the engineers all the tools possible to achieve this, I also think that, so if you are not able to automate these tools with the knowledge that, for example, experienced workers could have, I think it would be impossible for one person to do all the tasks in just having the possible tools. The key here, in my opinion, is the automation of everything.
Anything you would add, Sebastian?
Yeah, I just think back in the time when I designed products and the customer just changed the material, so some material properties, and I was like, oh my God, I have to start from scratch. And yeah, so I would have been very happy about the solution from Ignacio, where you can predict the property and automatically adapt the design to the properties. And I just think about the possibility now to have an optimization, like tweaking the material composition together with the design of the component, and to really find the optimum between material composition and design to really create the optimal solution.
Maybe a follow-up question to that would be, how was the thermal management component developed, and how did low code help here?
Yeah, so the thermal management component was developed inside Synera, as you've seen. We have a lot of expertise in bio-inspired design. We actually, as we have shown, for example, in the BioFly project, we have worked, for example, with ABI, which is the Alfred Wegener Institute in Bremerhaven, where in my case, I went there for, let's say, learning bio-inspired design algorithms and workflows. So we used an adaptation of these workflows that we learned there to do this tree-like structure component. So we wanted also to, for the heatsink, we wanted to add as much surface as possible in contact with air, so we could dissipate more heat this way.
Yeah, and I think it was crucial to have the connection to all those tools that you would use traditionally in your manual process. Yeah, like to Procast, to the CAD, to the FE simulation. So
and also,
I think it's,
and also the easiness to change parameters and to see in real time how this design is changing while you change those parameters.
Maybe a follow-up question for you, Ignacio, how it was for TECNALIA or your department and across different departments, how using a tool like Synera enables a smooth collaboration between your department, but also different departments, also in terms of communication and updating parameters and so on and so forth. How did that work?
Yeah, that's quite interesting because as TECNALIA, we are a very big company. Many times we actually don't know what is doing the person that is beside you. So many times when we work with these automated tools, that we are able to connect many things that different people does, we are able to achieve like more complex and more optimized components. So I think that that's very interesting because, as I was saying, there is a very high lack of connection between what someone does, and this way we are able to, let's say, to put our force together to achieve the best solution possible.
I'm going to come back to that, Sebastian. Maybe you can also share your insights there. Maybe a question in between from Mario, which is it possible to use the methodology for more than one material at a time, e.g. for a composite material?
The composite materials are very hard to apply components because of its anisotropy, but also because, well, in my case, I'm a very metallic guy, let's say, and also my team, we work a lot with metals. I think there should be some models to predict the behavior of these composite materials, and I think that would be also very interesting. But in our case, again, we have the lack of knowledge in this sense.
Yeah, but I can say that other companies, they did not a prediction for the composites, but they did the design for automation of composite designs. So this is as Synera is a generic methodology how to automate processes. Also, the automation of composite designs is possible. But yeah, as you said, the prediction would be also cool thing. So maybe you have someone in TECNALIA you don't know yet.
Yeah, we do have a team working with composite materials. Yes.
Yeah, would be cool to integrate that in Synera as well. Yeah.
Sure. Yeah.
Hopefully, we'll have a follow-up webinar on that topic then. Let's see. Sebastian, going back to the question I asked Ignacio, which is on the collaboration bit, do you have some insights there that you want to share with the audience to ensure smooth collaboration using low code?
Yeah. So maybe in general, the whole idea is to put the knowledge together in workflows, and collaboration there is possible by, you saw like what Ignacio showed, different nodes or different sub workflows. And I guess Ignacio has those sub workflows consist of knowledge from different departments or different colleagues. So this is basically the way most of our customers work together. Like the expert in procast simulation creates a sub workflow that automates the procast simulation, and giving this to someone else who adds his workflow, puts it together, and so they create the knowledge and the automation over specific tasks and specific silos by creating workflows and combining workflows from different departments, from different people. Maybe Ignacio, you how many people work there together? What would you say?
I think well, for the models of materials prediction, I think almost the whole team in Thirmetal that I was mentioning, I think we are 16, 17 people. So almost everyone. And for the, well, I'm the expert in TECNALIA with Synera, so I was the one working, integrating everything there. So yeah,
So
a lot of people.
So you also created workflow for those who are not able or to do it in Synera. So okay,
yeah,
also a good way that not
trying
everyone
to
has to use
understand
it.
what everyone does and then trying to integrate it to Synera.
Ah, cool. Yeah.
We have two more questions and then we'll wrap it up, guys. One from Ego, which is, there is currently quite interest in different markets as in automotive about the influence of manufacturing process design and mechanical performance, for example, as crash behavior. I guess that this automation levels might help a lot. Any experience on chaining virtual manufacturing with crash simulation? It's a little bit of outside what we've discussed, but maybe Sebastian, you have some insights there.
Yeah, hot topic at the moment. So one example that I can talk about is the crash management system. So bumper beam and crash box together was optimized by a customer. The gap to the manufacturing, I would say, was not completely closed yet there, but they also added some constraints like maximum wall thicknesses are possible in the sheet metal forming and so on. So yeah, possible, but I would say not completely done yet. But would be cool to have a follow-up on how to integrate it there. Yeah, but definitely possible.
I've shared the contact details of Ignacio and Sebastian in the chat, so you can just reach out to them. I'm going to pack two questions into one, Ignacio, for you, which is going to be the last question. What industries have already benefited from the TECNALIA's workflow, and what trends will shape material design and process automation in the coming years?
Yeah, so right now we've worked for different industries. We've worked for space. We've worked for energy harvesting industries by redesigning and optimizing like structural components. But we also have worked or are working also currently in aeronautics for thermal management components, as we have shown with the heat exchanger. But we with this kind of methodologies, we are planning to explore also different physics. We would like also to explore, for example, the design of mechanisms. We would like to explore the design of electromagnetic components. We think that this methodology could be extendable to different industries, and together with Synera, I think we could achieve this.
Absolutely. I think there's a lot of good stuff to come. Again, thank you so much, Sebastian and Ignacio, for this webinar today. There will be definitely more to come. If people have any questions, I've put the contact details of Ignacio and Sebastian in the chat, but we'll have a follow-up email with the on-demand webinar and much more information, so you can also explore low-code automation for your problems. Again, thank you so much, guys, and hope to see you in the next webinar.